Hello everyone, myself Dr. Kouser, Assistant Professor of Computer Science. Welcome you all to Session 3 of System Software and Operating Systems course. The Session 3 is on instruction formats of IBM 360. Coming to the introduction to the instruction formats of IBM 360, let us see some background about how IBM 360 started. The IBM System 360 is a mainframe computer system family announced by IBM on April 7, 1964. It was the first family of computers designed to cover the complete range of applications from small to large, both commercial and scientific. The goal when creating the IBM 360 was to create a family concept where for the first time a single ISA or instruction set architecture could be used with older and newer machines in the same family. The IBM 360 is also called S360. The IBM 360 was historically important due to the following features. The first feature it had was forward and backward compatibility, that is, a family concept and extensive instruction set was supported. The second important feature was clear separation between architecture and its implementation. They were independent of each other. The third feature was integration of scientific and business efficiency. So the system could be used for both scientific as well as business purposes with equal efficiency. And the fourth important feature was it had extensive use of microprogramming. So with this background, here is an image in figure 3.1 where we can see the IBM machine. This is how it looked. You can see that the machine is huge in size, and obviously the memory capacity it had was very less, and also the computation power of the system was less. However, it had the four important features that we discussed. That's why the machine's architecture was popular. Now moving on to the instruction set architecture of IBM 360 or IBM 370. The IBM System 360 is a 32-bit machine with byte addressability and support for a variety of data types. The data types that were supported were byte, half word, word, double word, packed decimal and unpacked character strings. The System 360 had alignment restrictions. So these alignment restrictions were removed in the next version of IBM 360, the IBM System 370 architecture. Now moving on to the internal state of the IBM 360, it has the following components. It has 16 32-bit general purpose registers, and register 0 is special when used in an addressing mode, whereas 0 is always substituted. It also has 4 double precision 64-bit floating point registers, which are an important part of the internal state of this IBM 360. And it also contains a program status word or PSW, which holds the PC and also some control flags with condition codes. The later versions of the architecture extended this state with additional control registers. So if you remember, in the previous architectures that we discussed in the session 2 about SIC and SIC-XC, SIC had only 5 registers and SIC-XC had 5 plus 4, 9 registers. Here you see that the IBM 360 has more number of registers when compared to the SIC and SIC-XC. Moving on to the addressing modes and instruction formats. As late as 1979, memory cost was very high, that is $75,000 per megabyte. As a result, a small System 360 might ship with only 16 kilobytes to 64 kilobytes installed. So the 16 kilobytes to 64 kilobytes was the huge memory way back in 1979. But now if you take just one picture on your phone, the memory that is utilized is almost 10 times the memory that was present in the IBM 360 machine. With that context, the design emphasis was on an instruction set that made the most efficient use of memory. For this reason, the S360 instruction set provides for instruction lengths of 2 bytes, 4 bytes and 6 bytes. We will see which instruction formats utilizes how many bytes next. The IBM 360 and 370 architectures have 5 different instruction formats. Each format is associated with a single addressing mode and has a set of operations defined for that particular format. While some operations are defined in multiple formats, most of them are not. These formats are classified by length in bytes, use of the base register and object code format. So the 5 instruction classes that are used to the general user are listed below. The first format is the RR format, which makes use of 2 bytes of memory. And the use of this RR format is for register to register transfers. And the next type of format is the RS. Here the use is register to storage and register from storage. Okay, this supports register to storage and register from storage transfers, and the length of this format is 4 bytes. RX is also 4 bytes and it supports register to indexed storage and register from indexed storage transfers. SI is the next type of instruction class which is also 4 bytes in length and it supports storage immediate transfers. And S&S is the storage to storage transfers, and this takes the maximum memory, that is 6 bytes. We begin by noting that the opcode or the machine code representation of each instruction has a length of exactly 1 byte. Here the 8 bits to represent the opcode. This allows for 256 different operations, more if an extra encoding scheme is used. This 256 because 2 to the power of 8 bits gives you 256 different operations. Now if you consider the register to register transfer instructions, since there are only 16 registers, each register can be fully specified by a 4-bit hexadecimal digit and 1 byte will suffice to specify the 2 registers. Thus, the specification of 1 operation and 2 registers would require only 2 bytes. That is why the register to register transfers requires only 2 bytes of memory. Consider the mechanism used to specify an address. It calls for base address which is encoded in 4 bits and 12-bit address offset encoded in 12 bits for a total of 16 bits or 2 bytes. Given that the operation must specify a source or destination register, the sum grows to 20 bytes. From 16 it grows to 20 bits. With the addition of an 8-bit opcode, it becomes 28 bits or 3.5 bytes. So the fractional part is not accommodated in memory. Therefore, you will have to go to the next possible integer, which is the 4 bytes. 4 bytes is nothing but 32 bits. Therefore, the instruction is expanded to include 2 registers. The encoding is then 8 bits for the opcode, 8 bits for 2 source or destination registers, and 16 bits are used for address, therefore accounting to 4 bytes in total. So here in this figure 3.2, you can see the address modes and instruction formats which are used in IBM 360. The first format, like already discussed, it is the R and R register format, and we know that it makes use of only 2 bytes of memory. The first 8 bits are used for opcode, and the remaining 8 bits are divided among register 1 and register 2 with 4 bits each. The next type of instruction format is the RX format, which is the register indexed format, which is 4 bytes in length. The 8 bits are used for opcode, and then the remaining 8 bits are divided between R1 and X2. X2 is the index register here, and then the remaining 2 bytes for the source and destination. The source is the base register B2 and the destination is D2, accounting to total 5 bytes of memory. And the next type of instruction is the RS format instruction, which is register to storage instruction. Here even this is of 4 bytes length, and the division is here you don't have an index register. We make use of 2 registers R1 and R3 and also a source and destination registers, and the division of memory is similar to that of the RX format. Here in the fourth type of format, that is the storage immediate format, here you have 8 bits for opcode, but here you don't have 2 registers because it is immediate instruction. So the immediate instruction itself occupies 8 bits followed by the base and destination of 8 bits each, accounting to 4 bytes of total memory. And then the last type of format is the SS format, which is storage to storage format, and we discussed that it is of total 6 bytes in length. Let's see how the division is. Opcode takes 8 bits as usual, and the length takes 8 bits followed by, because it is storage to storage, you will have 2 devices, therefore 2 source or base registers followed by 2 destinations should be given. Therefore the additional 2 bytes B1 D1 and B2 D2. So this is about the 5 different formats which are supported by IBM 360 and also IBM 370. Now we will learn about each of these formats with an example each. Here is the first type of instruction format, that is the register to register format. The register to register format, like already discussed, is a 2 byte instruction of the form operand register 1, register 2. The first byte contains 8-bit instruction code. The second byte contains 2 4-bit fields, each of which encodes a register number. This instruction format is used to process data between registers, 2 registers. So in this example AR6, 8, it adds the contents of register 8 to the register 6. Similarly AR10, 11 adds the contents of register 11 to the register 10. And the next type of format, register to storage format. This is a 4-byte instruction of the form operand R1, R3, D2 within brackets B2, which is destination followed by the source or the base register. Here is an example. Load multiple operation code is equal to x98. Suppose the label FW3, which is holding 3 32-bit full words, is at an address specified by offset x100 from base register R7. Then the instruction that is used is LM R5, R7 FW3 9857 7100. So the description below, I explain what this instruction means. Unpacking the object code, we again find the parts. The operation code is x98, which is for load multiple, which indicates multiple register load. The next byte has value x57, which indicates 2 registers R5 and R7. Here it is used to represent a range of 3 registers R3, R6 and R7. The last 2 bytes contain the address of the label FW3. The 2 bytes 7100 indicate that the base address is contained in register R7 and that the displacement from the base address is x100. The next type of instruction is the register to index storage format. This is also a 4-byte instruction of form operand R1 destination with the indexed address as well as the base register, indexed registers and the base register. The first byte contains 8-bit instruction code. The second byte contains 2-bit fields, each of which encodes a register number. The RX format using an index register, here we shall suppose that we want register 7 to be an index register. Consider the 3-line sequence of instructions in which R7 is given the value 4 to index from address FW1. If you consider this example, LR7 comma is equal to F of 4, here the register 7 gets the value 4. Similarly, LR4 comma FW1, here the operation code X78 gets executed. So this is about register indexed storage format. Here you can also have another type in the register index storage, which is register indexed storage with explicit base register. You can see the difference in the format. Operand R1D2 within brackets X2 B2. Even this is a 4-byte instruction of the form operand R1 D2 of X2 comma B2. The second byte contains 2 4-bit fields, each of which encodes a register number. The first hexadecimal digit is denoted by R1. This identifies the register to be used as either the source or the destination for the data. And the second hexadecimal digit denoted by X2 identifies the register to be used as the index register. If the value is 0, then the index addressing is not used. If the value is 1, then the index addressing is used. The third and fourth bytes contain a standard address in base or the displacement format. We now consider the source code formats that use an explicit base register. Here is an example. L load full word. Okay, L will load the full word. A will add the full word. Here the opcode is X58 for loading. For addition, the opcode is X5A. Moving on to the fourth type of instruction format, that is the storage immediate. Even this is a 4-byte instruction of the form operand destination within bracket base comma I2, that is the immediate register. The first byte contains the 8-bit instruction code as usual. The second byte contains the 8-bit value of the second operand, which is treated as an intermediate operand. The instruction contains the value of the operand, not its address. This we have to keep in mind. The first operand is an address specified in standard base register and displacement form. So here we have listed 2 instances of the instructions, which is MVI and CLI. MVI is to move immediate, CLI is to do immediate comparison, compare immediate. So this is about the storage immediate format. Now let us learn about the last format, last type, that is the storage to storage instructions. There are 2 formats for storage to storage instructions, and each of these formats require 6 bytes for the instruction object code. So the first type of the storage to storage instruction is the character instruction, and these are of the form OPD1 within bracket L comma B1 comma D2 B2. Here you see there are 2 base registers and also 2 destination registers which provide a length for only one operand. The length is specified as an 8-bit byte. The example for the character instruction storage to storage format is MVC, which helps you to move the characters. CLC command is used to compare the characters. And the second type of storage to storage instruction is the packed decimal instruction. These are of the form operand D1, L1 B1, D2, L2 B2, which provides a length for each of these 2 operands. Each length is specified as a 4-bit hexadecimal digit. Some of the examples of the packed decimal instruction of storage to storage format are ZAP, which is 0 and add packed, AP to add packed, CP to compare packed. So with this we complete the session 3 on IBM 360 instruction formats. In this session, we have learnt about what exactly the IBM 360 architecture looks like and also the 5 different instruction formats which are supported by the IBM 360 or IBM 370 machine with also its examples. Thank you all for your patient listening.